Hello everyone, welcome back to lesson number 18 for related rates. This is just two extra questions if you want to see how to do them. These two questions are very similar to the two problems that we did in video number 1. So whenever doing related rates with trig, the first thing is when you read the question, again, visuals are great, and then figure out what trig function to use. And then after that, we just start implicitly differentiating and plugging stuff in. So this one says Batman's plane is flying west at 500 feet per second. So we're going to go ahead and go directions here. So maybe a little vector. We don't have to worry about vectors, but this is 500 feet. So I'm going to go ahead and do 500 feet per second. And I'll go ahead and draw ourselves a little plane. So I'm going to go ahead and call this x, right? I like the horizontal to be x. So I know that the change in x with respect to time is going to be equal to 500 feet per second. It says that there's an altitude of this plane of 4,000 feet. So we're going to call that y. Right, and here's our ground. Here's our ground. So y is just going to be 4,000 feet. And the other thing we're going to say really quickly is we're going to make the assumption as we read the question that the plane's going to always be flying west. It's not going to be going up. It's not going to be going down. So this change in y with respect to time, and we do want to read the question to make sure that we're correct on this, that it's not descending or ascending, but we're going to make the assumption that it's flying west here, so our change in y is going to be 0, right? So again, that means that y is constant. So the plane is tracked by a searchlight on the ground, so let's go ahead and draw our little searchlight. There is that horrible searchlight. And if the light is to be trained on the plane, all right, find the change in the angle of elevation. So we have to create ourselves a right triangle here. And here is our angle of elevation. Again, it's from the horizontal looking up. So find the change in the angle of elevation. So we need to figure out what date the change in theta with respect to time is. At the same time, when the horizontal distance, at the time when the horizontal distance from the plane and the light is 2,000 feet. So the horizontal distance, which would just be any horizontal line right here. So I draw a line here and here, this distance would be the 2,000. So that basically just means that x is going to be equal to 2,000. All right, so we can go ahead and make this x, and we can make this 2,000 feet. So we automatically now have a right triangle. And you guys know that if it asked for, like, this the angle depression, this angle right here, just a side note, would be equal to this angle right here, because these are parallel lines, these are alternate interior angles, but yada, yada, yada. We have enough that we have enough for this problem, right? We have enough to solve for this. So like many examples before, we know the change in y and we know the change in x. So what trig function do we use? Well, the answer again is going to be tangent. Tangent of theta is going to be equal to the opposite side over the adjacent side. So in this case, our theta is down here, so it's the opposite side of the adjacent side. Because our y is actually going to be constant, then we're going to rewrite this as the tangent of theta is equal to y, which is 4,000, all over x. So this is the first example where it's not some number, 1 over some number times x. So we actually have to kind of sort of do the quotient rule here, but not really. It's pretty easy to do because we can rewrite this, by the way. So no quotient rule. We can rewrite this as 4,000 x to the negative 1. All right, so that's the function that we have for this. That's the function I'm choosing to use here. So now, hopefully that makes sense. We're going to implicitly differentiate the rest of this. So we're going to get secant squared theta d theta dt. And this is just going to be negative 4,000 x to the negative 2 power, which I'm just going to go ahead and write it down like this, right? So this derivative, we need to see it, it's going to be negative 4,000 x to the negative 2. And then I'm just going to go ahead and just bring the negative 2 down, as we see right here. We automatically know what x is, right? We know x is 2,000, so we can square that. And we got to figure out what secant of theta is, right? Secant of theta is. And then from that, we can just plug into our function. So we know this is 2,000, and we know that this is 4,000. So in order to find our secant, we actually have to use Pythagorean theorem again, right? Pythagorean theorem again. When we do that, and this is again where you 100% have a calculator for this problem. When you do that, you're going to get that this is 2,000 square roots of 5, right? 2,000 square roots of 5. So now we have that. We can say that the cosine of theta is going to be equal to the adjacent side, which is 2,000, all over the hypotenuse, which is 2,000 square roots of 5. So this actually ends up becoming a pretty nice little problem. So if we were to simplify this really quickly, we would just get 1 over the square root of 5. Well, secant of theta is going to be equal to the square root of 5 over 1, and so secant is actually just going to end up being 5. It's going to be 5. How awesome is that? So we're at the negative 4,000 over x squared. Well, x was going to be 2,000 squared. And then when all is said and done, and with the brilliance of a calculator here, you're going to get that change in theta with respect to time actually simplifies down to just 1 over 10. A really nice 1 over 10 radians. And again, by the units by second. Okay, so that is the answer for that problem. So a little bit more work here. Again, I want to show you guys an example where the derivative was not just some number times x or some number times y, where you had to just, first of all, make sure that you take the derivative of that by rewriting it and then using the power rule. All right, hopefully you guys are good with that one. We're going to move right down to our last example of the lesson, which is example number 6. And again, it's just a straightforward question, just more practice. Okay, so example number 6 says a man walks along a straight path with a speed of 4 feet per second. So we have ourselves a path, we have ourselves a person, and they're walking along a straight path. So they're walking in this direction. So again, I'm going to call this direction x, and I'm going to go ahead and put it over here. So the change in x with respect to time is going to be equal to 4 feet per second. A searchlight is located on the ground 20 feet from the path. Okay, so then from the path, there's a searchlight, which is right here, and this is going to be 20 feet. So y is going to be 20 feet, right? And then our change in our y, because again, searchlight's not moving, nor is the path, is going to be 0. So again, the searchlight is located on the ground 20 feet from the path, and it's kept focused on the man. All right, so it's right now shining a light here, and so this is our really horrible looking right triangle. All right, so it's shining here, and it's following him as he walks this way. At what rate is the searchlight rotating? All right, so now we're looking to find this, and notice that this problem, our theta is up here. Right? When the man is 15 feet from the point on the path closest to the searchlight. And so this is where you always want to read your question first before you draw the pictures, all right? So that's how you knew that the searchlight was, it seems like, why did you know it was right here? Why isn't the searchlight right there? Well, he's 15 feet, so x is 15. He's 15 feet from the point where the searchlight's the closest to the street, which again, the closest between 2 points, right? So this is the closest it is going to be. If I draw a little bit longer here, then this is going to be a hypotenuse of a right triangle, so this is the closest. So that's how I knew already. So I basically read the question prior to doing the problem. All right, so we have everything we need to know. And, you know, I know we've done this now. I think this is our 6th example, and we have 5 times we have used tangent, right? Tangent is going to be our example. So tangent theta, and again, be careful with this. So the tangent's going to be the opposite side over the adjacent side, right? So tangent. So if you're not sure what to do with derivative or related rates for trig functions, tangent's probably going to be the best thing for us to do. But we did an example in video 1 where this was not tangent. But anyway, so tangent of this. Now again, we have a constant. We have a constant here, and that constant is y. So I can go ahead and just plug in what y is, and y is 20. So I'll go ahead and do the tangent of theta is equal to 1 over 20x. And then, ladies and gentlemen, this becomes the same old story that we've said in the previous examples. We're going to implicitly differentiate this, right? We're going to get tangent of theta equals secant squared theta, d theta dt. I'm going to get 1 over 20 dx dt. I know dxct is 4. So go ahead and replace that with 4. And now we just have to worry about what secant is. Secant of theta is. I went ahead and wrote the 25 here because we have to use Pythagorean theorem, right? So 15, 20, 25, that's a 3-4-5 ratio. So secant of theta is the same thing as, well, the reciprocal of cosine of theta. So remember, cosine of theta is going to be the adjacent side of theta. So that's going to be 20 all over the hypotenuse, which is going to be 25. So just to keep the numbers nice, maybe this isn't a calculator problem. This is just going to be 4 over 5. And so that means that secant of theta, right? Secant of theta is just going to be equal to 5 over 4. So then I can go ahead and square this, right? So I can square this and get that it's going to be 25 over 16. And after that, I can replace. And so we go ahead and replace that. And then when we do some math and we do a calculator, we can just realize that d theta over dt is going to be equal to, again, you can use a calculator for this, but 16 over 125 radians per second. And that is the answer to that problem. All right, so hopefully after this example, you guys have a really good idea of how to solve trig functions using related rates. All right, so that's done with this lesson, and I'll see you guys in the next one.